This is chapter 15, Continuity and Differentiability of Master Math Mentor's AP Calculus AV manual. We're going to be looking at the second part of that today, talking about differentiable. In calculus, we're interested in examining whether functions are differentiable or not. A function is differentiable if it is quote unquote smooth. It'll have no sharp points, or the tangent line is vertical. That won't be the case. So if we think about a train traveling on a set of tracks, a function is differentiable if that train remains on the tracks. If that roller coaster comes off the track or that train comes off the track, then it would not be differentiable in that case. Here's some definitions for differentiability. A function is differentiable at a point if f prime of c exists. If f prime of c exists. Differentiable on an interval. Functions differentiable on interval a to b if f prime of c exists for every value on that same interval. And a function is differentiable if f prime of c exists for every value on that interval. There are some functions that are differentiable everywhere. Polynomials, sine, cosine, and exponentials are differentiable functions because they're differentiable at every single x value. What happened? All right, since the function is differentiable at x equals c, it is smooth. That implies that it must also be continuous. So here's kind of like this logic idea that pops up here. Differentiability implies continuity. A differentiable function is continuous. A differentiable function must be continuous. A differentiable function must be continuous. But just because it's continuous doesn't mean it's differentiable. It is possible that it could be continuous and not differentiable. And if a function is not continuous, it cannot be. If a function is not continuous, it absolutely cannot be differentiable. We have two definitions here. When a curve meets at a cusp point, this right here would be considered a cusp point. And what's going to happen here is that the tangent line is going to be vertical. And we know vertical tangent lines have undefined slope. Therefore, it would not be differentiable there. Over here, we have this has a corner. And no matter how much we zoom in, it's always going to be a corner. And it would be really hard to draw the tangent line there because the tangent line doesn't exist. Like, would it be here? Would it be here? Would it be there? Would it be there? And there's just no tangent line there that exists. And we've talked about that previously. And that would be considered a corner point. Or a corner, and it's not differentiable at that corner. So f prime doesn't exist in that location. All right, so looking at some piecewise functions, we want to look at the point where the rule changes and see if it is differentiable there or not. So we wish to determine if piecewise functions are differentiable. To do this, we first need to check continuity. And if you not sure what continuity is, you need to go back and check part 1 of chapter 15 and watch that video first. Once we check if it's continuous, then we can check on the differentiability. In order to check to see if a function is differentiable, we need to check several things. We need to check that the limit as x approaches c from the left of the derivative is equal to the limit as x approaches c from the right of the derivative. And that has to be equal to f prime of the derivative at that location. So first we're going to check to see if it's continuous. And then we're basically going to do those same idea with the derivative. If the derivative is continuous, then the original function is differentiable. All right, so let's look at part A. Part A, we want to find where the rule changes at x is less than or equal to 2. So the first thing we need to check to see, is it continuous? Is this function a continuous function? So we're going to check the limit as x approaches 2 from the left. That would be this top function. So we get 2 squared minus 6 times 2 plus 10. You can type that in your calculator or figure that out without a calculator. That's 4 minus 12 plus 10. 4 minus 12 is -8. -8 plus 10 is 2. So then we would check the limit as x approaches 2 from the right of f of x. And we end up with 4 minus 2, which is also 2. So the limit as x approaches 2 of f of x equals 2. And f of 2, if we plug 2 back into the to this part right here where it says equal to 2, we're going to get 2 also. So that's also equal to f of 2. So here's what we know about part A so far. We know part A is continuous at x equals 2. Now to determine if it is differentiable at x equals 2, we're essentially going to do the exact same thing that we just did, but we're going to do it with the derivative instead of the original function. So first we need to take the derivative, and then once we take the derivative, we can look at the limits. So f prime of x would be equal to the derivative of x squared minus 6x is 2x minus 6, and that still is x is less than or equal to 2, and the derivative of 4 minus x is just -1, and that's for x is greater than 2. So we're going to check the limit as x approaches 2 of f prime of x from the left, and the limit as x approaches 2 from the right of f prime of x. If we look at this, the left side is going to be the top still, 2 times 2 minus 6. 2 times 2 minus 6 is equal to -2. The left side is going to be -1 all the time. So -1. And those two are not equal. And since those two are not equal, we know our function is continuous at x equals 2, but it is not differentiable. It is continuous at x equals 2, but it is not differentiable at x equals 2. Part B, we're going to look at the same thing. We're going to look at the limit as x approaches 1, -1 from the left of f of x, and the limit as x approaches -1 from the right of f of x. So we're going to plug in -1 into the top function, -1 squared plus -1 minus 3. That is equal to -3. We're going to plug -1 into the bottom function. We get -1 minus 4. It's really +1 minus 4, which is also -3. And if we were to plug -1 into the top function, we would get -3 as well. So we know the limit as x approaches 1 of f of x is equal to f of -1, which is equal to -3. So we know this function is continuous at x equals -1. Now we're going to check to see if it is differentiable. So the first thing we need to do is find the derivative, f prime of x. The derivative is going to be equal to 2x plus 1 for when x is less than or equal to -1, and -1 for when x is greater than -1. So we're going to check the limit as x approaches -1 from the left of the derivative. We're going to plug in -1 into the top function because that's approaching it from the left. So we get 2 times -1 plus 1. 2 times -1 plus 1 is -1. And the limit as x approaches -1 from the right of the derivative would be -1. Since those are equal, and since that also equals f prime of -1, if we were to look, we would plug it into this top function because that's less than or equal to. We would get 2 times -1 plus 1, which is -1. So since those things are equal in this case, we know that it's continuous at x equals -1 and differentiable at x equals -1. So if we said it was differentiable, that implies that it's also continuous. Just because it's continuous, as we saw in part A, does not mean it's differentiable. Alrighty, we got part C. We're looking at the limit as x approaches 4 from the left of f of x, and the limit as x approaches 4 from the right of f of x. So we're going to plug 4 into the first equation. We get 2 minus the cubed roots of 4 minus 4, which is just 2. And then we're going to plug 4 in. We get the square root of 4 plus 5 for the right side. And that's equal to the square root of 9, which is 3. Those are not equal. Since those are not equal, we know this is not continuous. And any function that is not continuous also cannot be differentiable. So I don't have to do anything else to check for differentiability because I know it's not continuous. I know it's also not differentiable at x equals 4. All right, let's look at part D. We're going to take the limit as x approaches 0 from the left and the limit as x approaches 0 from the right. The limit as x approaches 0 from the left is going to be 0 minus 3 times 0 squared, which is 0. The right side would be sine of 0, and sine of 0 is also 0. And f of 0, we plug 0 into this function to find that. That's also 0. So what do we know so far? We know this function is continuous at x equals 0. But continuity doesn't imply differentiability. So we also have to check to see if it is differentiable. So the first thing we're going to do is find the derivative. And then we're going to check the limits for that. So f prime of x, derivative of x minus 3x squared would be 1 minus 6x. And that's for when x is less than or equal to 0. Derivative of sine x is cosine x. And that's for when x is greater than 0. So now we check the limit as x approaches 0 from the left of the derivative. And that's going to be equal to 1 minus 6 times 0, which is equal to 1. We also check the limit as x approaches 0 from the right of f prime of x. That's going to be equal to cosine of 0. And cosine of 0 is also 1. And f prime of 0, we would use the top function because that's greater than or equal to, would be 1 minus 6 times 0, which is also equal to 1. And since all of those things are equal, we know it's continuous at x equals 0, and we can now say that it would be differentiable at x equals 0 as well. You can graph these on the graphing calculator. Just type into YouTube how to graph piecewise functions on the TI-84, and it'll pull it up for you, and it'll show you how to graph those. I'm skipping that for this. I'm assuming that you would be able to do that on your own. Number 9, find the values of a and b that make the function differentiable. Well, we're going to have 2 equations in this case. The first equation, it's got to be continuous. So the limit as x approaches 1 of f of x from the left has to equal the limit as x approaches 1 from the right. And then we also know if it's differentiable, the limit as x approaches 1 from the left of f prime of x has to equal the limit as x approaches 1 from the right of f prime of x. So we're going to get a series of equations here, a system of equations that we can then solve for x. All right, so we're going to plug 1 into the left side. For x, we're plugging in for x, so we get a times 1 squared. A times 1 squared plus 1 is equal to b times 1 minus 3. So it's going to be a plus 1 is equal to b minus 3. It might help to solve for one of these. Let's solve for a. So subtract 1. We get a equals b minus 4. But we can't solve for a and b in this case because we got 2 unknowns at this point and only 1 equation. So that leads me to the second equation. We do need the derivative of this. The derivative of this would be 2ax, and the derivative of bx would just be b. So we're going to plug 1 into that. So our second equation is going to be 2a times 1 is equal to just b. So 2a is equal to b. And now we can plug that back in over here to solve this system of equations. So we get 2a equals b, we get a equals b minus 4. So we can plug b minus 4 in right there. So we get 2 times b minus 4 using the substitution method is equal to b. So we get 2b minus 8 is equal to b. I would move this 8 over here, move that b over here. So we're going to subtract b from both sides, add 8 to both sides. So we get b equals positive 8. And if b equals 8, we can plug that in up here. So a would equal 8 minus 4. So a would equal 4. So our two numbers are going to be a equals 4 and b equals 8 would be the two numbers that would make this function both differentiable and continuous. Remember, if it's differentiable, it is also continuous. But if it's continuous, it may or may not be differentiable. All right, same idea for part B. We got the limit as x approaches 2 from the left of f of x. That has to equal the limit as x approaches 2 from the right of f of x. So we're going to plug 2 in for the x value. So we get a times 2 to the third would be 8a plus 1. We're going to plug 2 in right here. We get 2 minus 3 is negative 1. Negative 1 squared is positive 1. So we get 8a plus 1 is equal to b. Plus 10. I forgot the plus 10 part. B plus 10. All right, so 8a is equal to 1. We can solve for b, subtract 10 from both sides. So we get 8a minus 9 is equal to b. We do the same thing for the derivative. The derivative right here would be 3ax squared. The derivative in the denominator, we could use chain rule if we wanted to. That would be b times 2 times x minus 3 raised to the first power times the derivative of x is just 1. So then we plug 2 into that. So we're going to plug 2 in right here and 2 in right there. So we end up with 3a times 2 squared is equal to 3a times 2 squared is equal to 2b times 1 minus 3 is negative 1. So we get 4 times 3 is 12a is equal to negative 2b. Divide both sides by negative 2. So we get negative 6a is equal to b. And then we can set those equal to each other. Since this equation is equal to b and this equation is equal to b, we get 8a minus 9 is equal to negative 6a. We can add 6a to both sides and add 9 to both sides. So we get 14a is equal to 9 and divide both sides by 14. We get a is equal to 9 over 14. We can now plug that back in. Might be easier to plug it into that equation. So b would be equal to negative 6 times 9 over 14. And that would be negative 54 over 14. We can divide by 2. We get negative 3 over 7. Negative 3 times 9 is negative 27 over 7. So b is negative 27 over 7. And a is 9 over 14. So we have to check and set the limits of f of x and the limits of f prime of x equal to each other to end up with our system of equations. And then we can solve that system. If you have any questions, please let me know. But we are done with chapter 15, continuity and differentiability. At this point, you should be able to do all of your homework. If you got any questions about that, you can reach out and I will try to help you if I can.